If you've not already read through the PDF that reviews the properties, the algebraic properties of inverse functions, please make sure you do that. Also, at the bottom of that PDF, it has a couple of examples of derivatives of inverse functions, just using y equals x squared and y equals the square root of x. And we see this pattern where the derivatives of the inverse functions at the corresponding points are reciprocals of each other, okay? The important thing there is it's not that the derivative at the same x coordinate is the reciprocal. In other words, like f prime of 2 is not equal to the reciprocal of f inverse prime of 2, but we have to use corresponding points. So what we're going to do here is we're going to go through and prove develop a relationship between the derivative of two inverse functions in a general sense, and then look at how we can apply that. So to begin, I'm going to sketch part of two inverse functions, so just generic functions here. We'll call this f, and then reflecting across y equals x. We're just a rough sketch here. This is going to be g, okay? And they are inverses of each other, so we have a bunch of corresponding points. So if I put a point right here on g, this could be written as x comma g of x. That is going to correspond to a point across the line y equals x that we could then label as g of x comma x, and those ordered pairs are going to be a big deal. Okay, so as we move forward, we need to be thinking about how the ordered pairs that correspond to each other on inverse functions have the x and y coordinates switched. Okay, all right, so because these are inverses, we know from algebra that f of g of x, or a composition of the two functions in either order, but I'm going to write it in this order, is going to be equal to x. Okay, a composition of inverse functions is always going to give us an output of just plain old 1x, okay? All right, so if I want to take the derivative of this function, okay, I'm going to take the derivative with respect to x. I need to use the chain rule over here because we have a composition. So applying the chain rule, I'm going to have f prime of g of x times g prime of x, again using the chain rule here. And then over on this side, I just have a 1. Okay, so let's say that I know what my equation for f of x is, or maybe I don't even know the equation. Maybe I just have some ordered pairs that are on f of x, and I know some derivatives that are on f of x, but I don't know anything about g of x other than it is the inverse of f of x. I still want to be able to take the derivative of the g of x function at a specific point. So if I'm looking at this equation here and I want to solve for g prime of x, I can divide both sides by f prime of g of x, and I get g prime of x is equal to 1 over f prime of g of x. Okay, so this tells me that if I'm trying to find the derivative of a specific point on the g function, I don't actually need to know what the equation for g of x is, because I can find the reciprocal of the derivative of the corresponding point. Okay, so this right here is the reciprocal of the derivative of the corresponding point on f. In other words, if I'm trying to find the slope of the tangent line right here, okay, I don't actually need to know the equation or anything about this other than the ordered pair that corresponds to that pair, because then if I can find the slope of the tangent line at this point, then I just find the reciprocal. Okay, so let's do a couple examples with this. And like I said before, the ordered pairs are going to be a really big deal. So I'm going to strongly recommend that you start by writing what your ordered pairs are. Not just writing the corresponding ordered pairs, but actually identifying this ordered pair is on this function and it corresponds to this other ordered pair on the other function. Because this is not a complicated topic unless you are not writing out your ordered pairs, okay? So I can't stress that enough, and I'll show you what I mean. So we've got this function, y equals x to the fourth plus 3x squared plus 2. Algebraically, I cannot rewrite this function and solve for the new y. So I can't write this as x equals y to the fourth, don't write this down, plus 3y squared plus 2, and then try and solve for y. I cannot do that. So don't try to write the inverse function, okay? Don't even try to write that algebraically, okay? I don't want you to say, oh, well, we'll just write the other function and then take the derivative. The whole point of this is that we can't always write the inverse function, okay? All right, so what we're going to do is we're going to talk about the ordered pairs. We're looking for the derivative of the inverse function, so we're looking for the derivative of y inverse, or you can write f inverse, that's fine, at the point 6, 1, okay? So first thing we need to ask ourselves is 6, 1 the ordered pair on the original function, or is it on the inverse function? Okay, and I have two ways that you can answer this. Thing number one is that you can't be asked to write the derivative of or to find the derivative of a function at a point if that point is not on your function. Okay, so what I mean by that is I'm not going to say, hey, here's f of x, find f prime of x over at this point right here, because that point is not even on this graph. Okay, so because we are finding the derivative of the inverse at this point, that means that the ordered pair 6, 1 has to be on the inverse function. Okay, now let's say that we got a little turned around, like is it 6, 1 or is that on the original, is that on the inverse? Go back to your original function, plug in 6. Do you get 1? No, you do not, okay? If we plug in 6 to this, 6 to the 4th plus 3 times 6 squared plus 2 is definitely not going to be equal to 1, okay? So that should tell you right there that 6, 1 is not on the original function. It has to be on the inverse, okay? Now, if 6, 1 is on y inverse, then that means that it corresponds to the point 1, 6 on the original function y, because we switched the x and the y coordinates. So the very first thing I want to do, even if I don't know both of the coordinates, like maybe I just have at x equals 6, I'm still going to write 6 comma something and identify that as being, remember this symbol right here means is in the set of, or on the interval, or in the element, okay, or is an element of, okay, but 6, 1 is part of the function y inverse, and then that means I also am going to write this out, 1, 6 has to be on the function y. Okay, so then because we know that 6, 1 is the point that is on y inverse, I'm now going to use this formula right here to find the derivative of y inverse at that point. So, and I am writing out a full statement, okay? Those of you that have a tendency just to kind of have random scribbled numbers and letters in various spots, this is not the time to do that. Really, no time is the time to do that. But please make sure that you are organizing your work and not labeling as in you need to write a statement about it, but labeling like you're writing full statements, okay? So I'm going to write that y inverse prime of 6, okay, so that's my y inverse is my g function from up above. Our point is at 6, and that's going to be equal to 1 over the original function's derivative at, and now here's the important thing, the corresponding x value on y is x equals 1. So these two numbers should never be the same thing. Oh, that looks like an exclamation mark now. There we go. Okay, these two numbers should never be the same. All right, at this point I can evaluate, so I'm going to come down below. So we have 1 over, and now I need to find y prime. So using the power rule here, we've got 4x cubed plus 6x, and then we are evaluating this, so this is such that x equals 1. We're plugging 1 into that derivative. So 1 over 4 plus 6, which is 1/10. Okay, so the derivative of y inverse at the ordered pair 6, 1 is 1/10. Okay, let's do another one. We've got y equals sine x on the interval from -2 to 2, and we want to find the derivative of y inverse at 1/2. Now this one's a little bit different because it doesn't give us a full ordered pair, it only gives us one value. But if I say find the derivative of a function f of x at 3, I'm always talking about the x value, okay? So that means that 1/2 is the x coordinate on the function y inverse. Okay, and remember we start by writing the ordered pairs. So I don't know what that is yet, but I know it's going to be something. And then that corresponds to the point something, whatever goes in this spot is also in this spot, comma 1/2 being on the original function y. Okay, now here's the thing about this function. We already know that we can write sine inverse as a function, okay? And we already know how to take the derivative of sine inverse, all right? And so we can actually use what we know about the derivative of sine inverse to check our derivative using this process. But in this case, excuse me, in this case, I do want to go through this using the derivative of the inverse theorem that we are looking at today. Okay, so if we're only given one x coordinate, go back to your original function and ask yourself sine of what is equal to 1/2. Okay, sine of what is equal to 1/2, and the answer to that is pi over 6. So that means pi over 6 goes in both of these spots. Okay, and yes, we are always in radians. Okay, so then if I want to find y inverse prime of 1/2, this is going to be equal to 1 over y prime of pi over 6. Okay, again, I'm writing out a full statement. Okay, and so then that becomes 1 over, and now the derivative of the original function is cosine x, and we are evaluating when x is equal to pi over 6. So 1 over cosine of pi over 6 is going to be 1 over root 3 over 2, which is 2 over root 3. Okay, now I did say that this is one that we could use our what we know about the derivative of sine inverse to check. So I'm going to do that real quick. So if we say that y inverse is equal to sine inverse of x, and then we want to find the derivative at 1/2. Okay, so then y inverse prime of 1/2 is going to be 1 over root 1 minus x squared at x equals 1/2, which is 1 over 1 minus 1/4 would be 3/4, so that's root 3/4, which is 2 over root 3. So we get the same thing, okay? In this case, yes, we were able to actually write the inverse function, but as a rule, do not try to do that. I just wanted to show you that one so that it was one that we could write the inverse of to check how this property is working correctly, okay? All right, if you want to stop here and try the next one, that's a good idea. All right, I'm going to go ahead and go through this and move that over a little bit so we can see the rest of the question. Okay, so we're given that f of x is equal to x to the 7th plus 3x to the 4th minus 5x squared plus 3. Here we are looking for the equation of the tangent line at the point x equals 2. So again, we start by asking ourselves, is x equals 2 a point on f inverse or on f? Okay, and here it doesn't give a full ordered pair, but the x coordinate is always going to be the x value of the function that we are differentiating, meaning x equals 2 is the x coordinate on f inverse, okay? So again, we have 2 something is on f inverse, which means that something comma 2 is on the original function f. Now, we do need to figure out what goes here. So we go back to the original equation. I am strongly urging you not to plug 2 in here and then try and solve. Okay, that's not going to work. If I have a 2 over here, I mean, there's no. This is a degree 7 problem. I'm definitely not going to be solving that by hand. Okay, and I don't have a calculator for these problems anyway. So this is the method this is what the book calls by inspection, which is really just a fancy way to say guess and check. All right, and when you are guessing and checking, I'm going to strongly recommend that you don't guess something like, like root 7 or something to start with. Start with a number like 1, okay? If 1 doesn't work, maybe try 0, all right? If it's a trig function, then yeah, probably try 0 somewhere. But really, if you just guess 1 or 0, almost 100% of the time, it's going to be one of those. So I'm going to look at this and I'm going to guess 1. So if x is equal to 1, then I've got 1 plus 3 minus 5 plus 3, which is 7 minus 5, which is equal to 2. Hey, look at that, it worked. Okay, so that means 1 goes in this spot and then also in this spot. Okay. Again, my guessing and checking was plugging into the original function because I can't actually write the inverse function. Okay, so now we are looking for the equation of the tangent line, meaning we need a slope and we need a point. All right, so to get our slope, we're going to start with f inverse prime of, and then the x coordinate here is 2, and that's equal to 1 over the derivative of the original function at the corresponding point, which is 1. Okay, so then 1 over, and then taking the derivative, that's 7x to the 6th plus 12x cubed minus 10x at the point when x is equal to 1. So we get 1 over 7 plus 12 minus 10 is 7 plus 2, so 1 over 9. Now we're not quite done here. This is just our slope, okay? We still need to write the equation, meaning we need an ordered pair, okay? So important point right here. When we are writing the ordered pair, remember that we're writing the line that is tangent to F inverse, meaning we need a point that is on F inverse, okay? So we use this one because this is the point that is on F inverse. So the equation of the line is y minus 1 equals the slope 1/9 times x minus 2. And that's the equation of the line. Okay? I know there's no more on the form of the notes here, but I do want to show you one more example using a table problem, okay? So, for example, let's say that we have a table of values, and let's see, x, f of x, and let's do 2, 5, 9, 11, 11, 9, 5, 2, and I'm just making up some numbers here, and then f prime of x is going to be 6, -3, -4, 8. Okay, so we have some values for a function f, and we know that f is differentiable. That's going to be given to us in the problem, and we have 4 x coordinates, and we know their corresponding y values and the derivatives at those points. Okay, so if we say, all right, if f of g of x is equal to x, which right off the bat you should be asking yourself, what information is that telling me? That means that they are inverses. Okay, that means that they are inverses. So if f of g of x is equal to x, write the equation of the tangent line at x, we'll say of the line tangent to g at x equals 9. Okay? All right, so let's go through this here. So x equals 9, again, first thing we do is we write ordered pairs. So 9 comma something is on the inverse function, which is g of x, and that corresponds to something comma 9 on the original function f of x. As we know nothing about g of x, no ordered pairs, nothing other than f and g are inverses. Okay, and so first thing we do is we need to figure out what goes in here. Well, we don't know about f, so let's look at our chart. We don't know about g, so let's look at our chart for f. We can see that something comma 9 is a point on f of x. This right here is x equals 9 on the original function. That is not what we want. We want the y value on the original function f to be 9. So I'm looking right here. Okay, so what x value corresponds to an output of 9 on f? It's going to be a 5. All right, and then if this is a 5, that means there's a 5 that goes right here. Okay, so then to write the equation of the line, we need a slope first. So we're going to do g prime of 9 is equal to 1 over f prime of the corresponding value, which is 5. Okay, so 1 over, and then do we know f prime of 5? Yes, we do. It's right here, -3. So the slope is -1/3. Okay, and again, writing the equation of the line, we use the point that is on the function that we are drawing the tangent line to. Okay, so y minus 5 equals -1/3 times x minus 9. Okay, let me know if you have any questions.